right, Andrew, what are we doing today?
Direct substitution.
Direct substitution. All right, let's have some fun. Today's gonna be good, Andrew. Today's good. Today's good. All right. Before we can even talk about this, we need to talk about real quick about continuity. Okay? Continuity. And this will be a recurring theme for the rest of the year. This is definitely something that is on the AP exam, and you will see it a lot, right? So continuity. And we talked about it yesterday, right? Andrew? We did talk about it yesterday. So here's the formal definition as we approach, or formal definition of continuity. Here we go. Okay? The limit of f of x as we approach c from the left and the right is going to equal that function value c. Okay? Now, just to give you a real quick visual of that, Andrew, what does it mean to be continuous? And we kind of talked about this yesterday. And I'll just reference our homework problem right here, right? The limit of this thing as we approach 2 from the left and the right is equal to 5, right?
Right.
When I approach 2 from the left, when I approach 2 from the right, our y values get closer and closer to 5. But here's my question. What happens, what is f of 2? If I say, what is f of 2, aka like f of c right here, what's f of 2? You have no idea. It's undefined, right? There's a hole there, Mr. Baker. There's a hole there. We don't know what f of 2 is. What is that, right? So, is this function continuous? No, because the limit from the left and the right did not equal f of 2, or f of c in this case, right? It doesn't equal. Now, what happens if you had something like this? Just again, kind of like that homework problem. Can f of 2 equal 3?
Yes.
Absolutely. Is it still continuous? Does the limit from the left and the right equal f of c, equal f of 2? Do those equal each other?
No.
No. So that is still not continuous. But Andrew, what happens if I just took this little dot right here and colored it in?
It becomes continuous.
It's continuous, right? There's no holes, jumps, or gaps. Continuous functions have no holes, jumps, asymptotes, gaps. It's good. That is a continuous function. Now, Andrew, when we take a quiz here coming up on Monday, we're one day closer, right?
Yeah.
The definition of continuity, how do they want you to write this on an AP exam, right? If the AP exam loves it, Mr. Baker loves it, and he's going to kind of hold you to the same, criteria. So let's break this down even further. The AP exam loves you to reference the left behavior and the right behavior. Doesn't this mean limit from the left and the right?
Yes.
So go ahead and talk about something, the limit as we approach c from the left, right? Needs to equal the limit as we approach c from the right. It also needs to equal that function value of c, okay? They love this on the AP exam. When they talk about continuity, holy cow, that's the expression that they want you to use. Talk about the left behavior, the right behavior, and the function value. Colin, do you know what most people leave off when they talk about continuity?
Function value.
They leave that off right there. They're like, Mr. Baker, the limit from the left and the right equal each other. It's continuous. But then I just draw a little picture like this, Colin, for them on the board. Yeah, the limit exists, but is it continuous? No, right? You got to reference that function value when you're talking about continuity. All right? Cool. I'm ready. Emily, where are you at? Gymnastics? I'm sorry. You were doing a double full.
Yeah.
Were you? Oh, okay. Something silly? Oh, it's okay. It's all right. It's all right. It's all right. It's all right. You got to take care of yourself, though. All right. Well, let's, Emily, let's do some direct substitution problems right here. Okay? We're going to have some fun today. I like these problems. All right. So, Emily, I want us to evaluate that limit at x equal, or as x approaches 2, right? We can do direct substitution today, Emily, because really, is this a parabola? Are parabolas continuous? Yeah, they are. Parabolas are continuous, meaning that there's no holes, jumps, or gaps, which means that I can do direct substitution. I can literally just plug 2 into this, and I'm gonna get an answer because I know it's somewhere on the parabola, right? So Emily, let's do some mental math. If I plugged in 2, what do you get? 9. 9 is correct. Emily, are there easy points like that on an EP exam? Yeah.
Oh, yeah.
Yeah, like FRQs, there's 6 of them, right? There's 6 FRQs on the AP exam. They're worth 9 points each. That would easily be 1 point out of the 9 on an FRQ. You know what I mean? Like, boom. You know what I'm saying? Feel good about that?
Yeah.
All right, cool. Hazel.
Yes.
Hazel, let's do it. Hazel, example 2 right here. All right, let's do this one. I'll be nice to you to get started.
Okay, good.
All right. Is cosine continuous? I'm just throwing that out there.
Yes.
It is. I mean, it's just a wave that goes on forever, right? Which means I can evaluate that limit really just by plugging in pi, using direct substitution. Do you remember what the cosine of pi is?
1, 0,
You were so close on the first one.
-1.
It is -1. Okay? If you just plugged in the pi, the cosine of pi, you get -1. Cool? Yeah, feel good about that? All right, let's go with, Avery? Avery, help me out right here. I just forgot, you know what I'm saying? Avery, what's that coordinate right there in the middle, in the first quadrant?
5/4.
The radian measure is pi over 4. What are the coordinates though? Avery, this is why we're talking about it. It's radical 2 over 2, right? Remy, don't help her. No, you can't. It's fine. It's radical 2 over 2, radical 2 over 2, right? Avery, you're not the only one, believe me. Okay? I just had to call on one person. This is why Mr. Baker's talking about it, Andrew, because some people might be a little rusty, right?
Yeah, right.
Yeah, that's all right. All right, so Avery, you want to do another one? What's this one down here? You can give me the radian angle. What is it?
√3/2.
Yeah.
1/2.
All right. What about this one over here?
1/2 √3/2.
Excellent. What's the radian measures for these?
Oh, pi over 3 and pi.
Which one's pi over 3? What's this
sorry,
one?
pi over 6.
Yeah. And pi over 3?
Yes.
All right, good. Hey, we're just knocking the dust off. You know, that's all we're doing. Does this need to be fast for everybody, Fox?
Yeah.
Yeah, it does, right? We just gotta get there. You know what I'm saying? You gotta get there. Columns are coming back to you.
Sir?
All right, that's good. Lucy. Lucy. You gotta make your brother proud on this one. Okay?
I don't think you'd have to be proud.
Wow. Let's make your brother proud. Okay? Mr. Baker throws a fastball like this at you. I want you to be able to hit it out of the ballpark. That's okay, Lucy. Now, Lucy, we're talking about this because, right, lots of things are going on.
Yeah.
Do all pi over 3 angles behave the same? You just got to figure out whether it's positive angles, right? Do all pi over 4, pi over 6 angles, they all behave the same, right?
Yeah.
It's like if you see a pi over 4 angle, it has something to do with that. Pi over 6 angle has something to do with that, right? So, Lucy, would you like me to share Mr. Baker's technique for thinking about this? Who wants to tell me right now that they know secant is 1 over cosine? Yeah, people do. People raise their hand. That's good. That's good. Do you think Mr. Baker thinks like that? I don't. You know what I mean? I don't. Is the unit circle like this? Is the unit circle in terms of sine and cosine? Right? Cosine is x. Sine is y. Right? The whole unit circle is in sine and cosine. Right, Lucy? So here's what I see. I see one, we're going to try direct substitution. Right? So what I see right here is not secant, but cosine. What's the cosine of 7 pi over 6? Well, 7 pi over 6 is just that angle like right here. So what's the cosine of 7 pi over 6? What is it?
Wait, is it √3/2?
It's negative radical 3 over 2, right? Like that comes to my mind. I think cosine of 7 pi over 6, ooh, that's negative radical 3 over 2. What do you think I do with my answer then when I have negative radical 3 over 2? I just flip it, right? Because I know secant is the opposite of it, right? So when I see secant, I just think cosine. I get my answer, and I flip it, right? So cosine of 7 pi over 6 is negative radical 3 over 2. You flip it, becomes negative 2 over radical 3. What are you supposed to do with that? What do we still have to do? We're not there yet. You have to square it, right? If you square that, that's how you're going to get 4/3 as your final answer, right? That would be essentially your y-coordinate of that secant squared graph at 7 pi over 6. Lucy, what do you think?
Sounds good.
Okay, and Lucy, you're going to see me a lot this year too, just so you know, like when we start talking about the chain rule and derivatives and all this other kind of fun stuff, right? You're going to see me write this kind of stuff on the board, so you can see, right, really secant squared is really just secant x squared, right? We found secant, and then we just squared it. Then we get the answer. That's coming. Okay? Good. Good. All right. Well, I don't think somebody else I haven't called on yet. Madison. Madison, how you doing?
Good.
That's good. All right, Madison, let's do another one. Madison, just for fun, what grade are you in?
I'm junior.
Junior. All right. Did you go to Page Middle?
No.
You didn't? That's fine. That's fine. Where'd you go?
I was in Texas.
Texas. All right. I lived in Texarkana at some point, if you consider that Texas. That was back when I was young, but all right, you're in Texas. Well, it's okay, Madison. You're not going to understand my reference here in just a moment, but there's a lot of people around you that will. All right, so Madison, I want you to find the limit as we approach 2 right here. This one right here. All right, what's the first line of defense with limits? What do you want to do first?
Factor.
Which should you always try first?
Substitution.
Direct substitution, right? You try direct substitution. If you plug 2 in right now, right? If you plug 2 in right now, you're going to have 2 squared minus 4 over 2 minus 2, right? What do you get, by the way?
0 over 0.
0 over 0, Madison. And Madison, what do we know about 0 over 0? What do we call that?
Undefined.
No.
Starts with an I. We talked about it yesterday.
Oh, indeterminate.
Indeterminate form, right? Indeterminate form, meaning that we got to do some more work. We don't know what it is, right? We don't know what it is. So, Madison, do you remember what this is called right here? Madison, you don't know much about me, but do you know who my algebra 1 teacher was back in the day? Her name is Miss Tidwell. She was the best. You know what I'm saying? So Madison, when you look at this right here, difference of squares, right? I remember learning that in her class all the time. She loved the A's and the B's and the blah, blah, whatever, right? So we did difference of squares. Do you remember how to factor that?
I think so.
How do you factor?
X minus 2. X plus 2.
Excellent. That's a difference of squares, right? We're making Miss Tidwell proud. She still does that to this day.
Yeah.
It's good. It's great. I love it. All right. So, Madison, these cancel out, right? You plug 2 in, and all of a sudden you get 4, right? You get 4. That is the limit of this function as we approach 2. Now, because 2 actually cancels out, Andrew, what do we know about 2 actually? What's happening at 2? There's actually a hole there, right? But you can still find the limit. Is this function continuous?
No.
No. No, it's not. But you can still find the limit. It's not continuous, but you can still find the limit. All right. Let's talk about some properties. Okay? Let's talk about some properties. Akshara, can you see the board back there today?
Yes.
I'm just checking out your well-being. My job is to teach you math, so I just want to make sure. All right, we got some properties real fast of limits. All right, properties of limits. All right, these two are going to be given to you to get started. All right. So, Akshara, I just told you that the limit of f as you approach c is L, right? The limit of g as you approach c is k. Cool with that?
Yeah.
All right, now, first property right here. If they gave you something like this, and this is just kind of like talking about all the common sense stuff that you guys are gonna just realize, okay? I'm throwing in this random letter b. B is just a constant. It can be whatever it wants to be. It can be a negative, a positive, a radical, a fraction, who cares, right? It can be whatever it wants to be. My question is, they're just multiplying right here. That's cool. If I saw something like this on the test, right? Do I know the limit of f as I approach c? Do I know the limit of f as I approach c?
Yeah.
What is it?
L.
It's L. So if I know the limit of f as we approach c is L, what do you think my answer is?
L. But
Times b. It's just BL, right? You would literally just take whatever number out there is multiplied, right? And you just multiply by that limit that you know of f, right? That's all you got to do. You just multiply, right? Akshar, what about this one? As we approach c, say of something like this. Okay? I'm just trying to kill two birds with one stone right here, right? Just break it down. Like almost go like just down the line. Go one step at a time. Do I know the limit of f as we approach c?
No.
It's L. Do I know the limit of g as I approach c?
K.
What do you think you're going to do in the middle?
L plus or minus.
Plus or minus. So you're just going to add or subtract them, right? You just go down the list and you're like, psh, this is just L plus or minus k, depending on what operation it is. Adding or subtracting, right? But again, you just kind of go down the list and you're like, I know this one, I know this one. Then do the operations at the very end, right? You can kind of know where this is going here, Akshara. If I'm going to do scalar multiplication, adding or subtracting, what do you think this next one is?
Division.
But we'll do division next.
Oh.
What do you think the answer is there? If you're ever just multiplying two functions together, do you still kind of like break it down, go one at a time? Yeah.
Times K.
Yeah, it's just L times K. I know the limit of both of those individually, and then I just do the operation. It's just L, K. And the same rules apply, right, if you were gonna do some division. If you had f of x over g of x, right, you would think, oh, it's just L over K, assuming that K doesn't equal 0, right? Assuming that K doesn't equal 0, because you don't wanna divide by 0, okay? So yeah, how do you feel about that? Right? Akshar, tonight on your homework, you might get something over 0, right? We don't know what the functions look like, obviously, up here. We don't know what f and g are. If you ever get something over 0, technically it's undefined.
No.
And really, for today, because we can't do any thorough investigation, your answer is D and E, right? Because the limit either exists or it doesn't exist, right? If something is undefined because you're dividing by 0, it doesn't exist. Okay? Andrew, you got that?
Okay.
All right. Andrew, we're going to finish with you today. I'm going to give you one example. I think this is example number 5. We'll just throw the whole kitchen sink at you, Andrew, because I know you can handle it. Okay? This kind of stuff makes sense to a lot of students every year, so this is a good thing. This is a nice lesson. All right. So Andrew, I told you the limit of f as you approach 2 is 5, the limit of g as you approach 2 is -2, and the limit of h as you approach 2 is 11. Right? Right. I can do one example and just be done with this, because here we go. It kind of entails everything that we've been doing. Right? You kind of get the idea. Andrew, how would you want to go about evaluating this limit?
I would plug in the 5, -2, and 11.
For F, G, and H?
Yes.
Right, you know the limit of F, you know the limit of G, you know the limit of H, you just plug them in, right? Perfect. Right, you're just doing your scalar multiplication. So notice how we're doing like the scalar multiplication, we're doing adding and subtracting over here, all of them can be combined. What do you get, by the way, Andrew, if I plug all these in?
Negative 33.
Negative 33. Good job, Andrew. All right. Madison, who was the best Algebra 1 teacher of all time? Oh, good memory. That's good. She was misused back in the day. Because it was a long time ago since Mr. Baker was in the 7th grade. Long time ago. Did everyone have Miss Tidwell? Yeah, I'm getting a lot of. Miss Durham's out there? She would teach still? No, Miss Durham's?
She was here before.
Year before us. Okay. All right. Cool. All right, well, that's it, Andrew. I'm going to set you loose.